Jai Shri Gurudev. Dear students, welcome to Module 4. Uh, in this module, we will analyze the stability of the system in time domain and frequency domain. The title of the module is Stability Analysis and Frequency Domain Analysis and Stability. So in this session, I'm going to cover two topics. First one is concept of stability, the basic introduction, and then we will take up an important criteria known as RH criteria, which is used to analyze the stability of the system. Coming to the content of the module, so in this module first we will discuss about stability concepts, necessary conditions for stability, RH stability criteria, followed by relative stability analysis using RH criteria. Then we are going to take up another important topic termed as root locus technique, which is also one of the time domain technique used to analyze the stability of the system in the S domain. Then we will start with the frequency domain analysis of the system, wherein we will discuss about correlation between time and frequency response, followed by another type of plots called as Bode's plots, which is used to analyze the stability of the system in the frequency domain. So finally we will take up some problems which helps us to determine the experimental determination of the transfer function. So this is the outline of module 4. So in today's session, let's take up the first two topics, that is basic concepts of stability and necessary conditions which we are going to apply for stability, followed by RH criteria. Now coming to RH stability criteria, it is defined as a method which is used for determining the continuous system stability. So the basic concepts of this RH criteria is that it determines the number of roots of the characteristic equation with positive real parts, which is equal to the number of changes in the sign of the first column of the roots array. So here we are going to construct an array called as roots array. So wherein the number of sign changes in the first column of the root array tells us how many roots lie in the positive half of the S plane. So that is what is done in RH stability criteria. Now this method basically deals the stability information without the need to solve the closed loop system poles. So that is, without determining the pole location of the poles, we can just judge whether a system is stable or unstable. And also we can also tell how many closed loop poles of the system they lie in the left half of the S plane or in the right half of the S plane along the j omega axis. Okay, so this method basically it requires two steps, that is generating a data table called as roots table and interpret the root table to tell how many closed loop poles are in the left half of the plane or right half of the plane in the j omega axis. Now this is the table which we are going to construct using the given characteristic equation. So here an example of an nth order characteristic equation is given. This is the equation that we are considering here. Now in this equation we have the coefficients named as a0, a1, a2, etc. up to an, which is considered as an nth order characteristic equation for a system. Now using this we are going to construct the roots table. So when we start the construction of the roots table, always you are supposed to start with the higher order of s, that is we'll start with s to the power n row. Now here I am going to consider the coefficients an. So you have to take alternate coefficients, then an minus 2, an minus 4. Similarly, after that I will be taking this value, that is s to the power n minus 1. Now we are going to consider the coefficients from this n, that is an minus 1, an minus 3, an minus 4, and so on. Now using these two rows, so these two rows are created, that the first and second rows are created by using the characteristic equation. Now we are going to follow a procedure which is used to construct the consecutive rows. The procedure is, you will be taking the first coefficient, that is a bar an. Okay, you keeping this as reference, we will be constructing the other values. So we will consider the first two rows. So take this element first for your reference. Now we will cross multiply this with this. So multiplication is taken like this, that is a n minus 1 is multiplied with a n minus 2, and that product is subtracted with a n into a n minus 3. So cross multiply so these two values, okay, this with this and this with this, and then divide that by a n minus 1. That gives me the value of b1. So this b1 is generated by this value. Now the same procedure is repeated for b2 also. So what we are going to do next is we will take a n minus 1, we will multiply now with a n minus 4, and a n minus 5 is multiplied with a n. Okay, so that you are going to get b2 as equal to a n minus 1 into a n minus 4 minus a n into a n minus 5 divided by a n minus 1. So this is giving me the value of the coefficient of the next row, that is b2. Next, similarly, the same procedure is repeated if you have consecutive elements. So now the next row, it is constructed using the second row and third row elements following the same procedure. That is, what we will do is, now we will take b1 as our reference. Okay, so we will cross multiply b1 with a n minus 3, b2 with a n minus 1. Then we will divide that by b1, so that this gives us the value c1. Now same procedure is repeated for the next values also. Now what I will do is, b1 is multiplied with a n minus 5, b3 is multiplied with a n minus 1, and then we are dividing that by b1. So this is giving us the value c2. Okay, so same procedure is repeated for the consecutive values, and this is array what we are going to create is called as the roots array, which is used to analyze the stability of the system. Now let's take an example and we'll see how to construct the root table. So we have an example here wherein the characteristic equation is nothing but obtained by equating the denominator to 0. So in the array, if you take this particular example here, you have the characteristic equation as a4 s to the power 4 plus a3 s cube plus a2 s square plus a1s plus a0. Now we have to start with the highest power of s, that is nothing but even power of s. So I'll start like this. So this is my first row coefficient which I'll be considering. Now take a4, leave a3, alternate values you must take, then take a2 and then a0. So even coefficients are taken here, and it is giving us the first row. In the first row we have a4, a2 and a0. Similarly, in the next step I'll be taking the s cube power, wherein the coefficients are taken as now as a3. I'll take a3, then a1. So if you don't have anything after this, then it is considered as 0. So the second row elements are nothing but now equal to, it is a3, a3, a1. So I don't have any other element, so it is 0. Now we are going to construct the consecutive rows using these two rows following the same procedure. That is, we are going to take determinant of a4, a2, a1, a3. It is nothing but equal to a3 into a2 minus a1 into a4 divided by a3. So s2 row is constructed, s1 row is constructed, and s0 row is similarly it is constructed. So once the array is available to us, then we can analyze the stability. Now coming to the important difficulties that we may come across when we start constructing a root array is, we have 4 different cases, important cases. So basically among them 3 important cases we are going to consider here. So one case is, sometimes case 1 is no element in the first column is 0. This is one case what I can have. The second case is a 0 in the first column, but some other elements of the row containing 0 in the first column are non-zero. Or you might have a case where entire row might become 0, which gives us erroneous result. So this must be avoided. So first let's take a case where no element in the first column is 0. So let's take an example here. So example is s cube plus 6s square plus 12s plus 8 equal to 0. So I'm vertically I'll be writing all the values of s starting from the highest power, that is s cube, s square, s to the power 1, s naught. Now when we are taking the coefficient, I'll take the coefficient of s cube is 1. So this coefficient you have to take coefficient of this I will take. So when I take these two coefficients, I have 1 and 2. So these are the coefficients corresponding to the row S cube. Okay. Now next is you have to start with S square. Now you need to take the power of S square and its coefficient. So now if I consider this, I have the coefficient as 6 here and 8 here. Okay, so I'm taking it and I'm trying to construct the next consecutive rows. So here when you start, I'll cross multiply 6 with 12 and then I'll subtract with this product. So 12 minus 6, 12 into 6 gives you the value as equal to how much? 72 minus 8 will give you the value as equal to 64 by 6, and the other value will be 0. And similarly, by using these two values, that is, I'll cross multiply this value with 8 and this with 0, so that you will be getting the next value as equal to 8. So this is the last value which I'm going to get. Remaining all other values are zeros for me. Okay, now using this, you're supposed to just check the stability of the system. Here as you can see, if you refer your first column, none of the elements are 0 and there are no sign changes. If this is the case, then the system is said to be stable. So you don't have a replacement here, you can directly consider this. So no 0 in the first column. So that is what I told. Since there are no sign changes in the first column and there are no values with this 0, so directly I can say that all the roots, they lie in the left half of the S plane, and none of the roots are in the right half of the S plane. So system is said to be stable. This is how we are going to analyze the stability of the system. So let's take another example. The task is you need to find the stability of the continuous time system having the characteristic polynomial of the third order. Then the equation is given as s cube plus s square plus 2s plus 4. We need to construct our roots table. So roots table is giving me the value in this form. Now you can observe that when I move from here to here, that is from here to here, there is no sign change. So 1 to minus, here there's one sign change, and minus to plus, again you have one sign change. So totally, if you can observe here, we have two sign changes. So the conclusion is, since there are two sign changes in the first column, the two roots of the characteristic equation, they lie in the right half of the S plane, hence the system is said to be unstable. So the hint is either everything should have the same sign, whether it could be positive or negative, but there should not be sign change from minus to plus, plus to minus, and so on. So that indicates the number of roots which lie in the right half of the S plane, and system is said to be unstable if you have any sign changes. Now coming to one more example, here this is an example where an unknown value k is there in the equation, and you are supposed to check for what value of k the system is said to be stable. This is one type of the question which is usually asked. Okay, so using this procedure, we will construct the table as usual. So you will get a first column like this. So this is our first column. So now I need to find out the value of k such that there are no sign changes. See, here in the question itself, it is given that you need to find out a value of k for which the system becomes stable. So for that purpose, I will assume that all the elements in the first column are positive. So I'll assume that my value 8 minus k by 3 is greater than 0, or you can consider 8 minus k to be greater than 0, and similarly 1 plus k should also be greater than 0, so that you will not have a sign change. Please to refer this. So for the system to be stable, the condition is that these two elements, that is 8 minus k by 3 and 1 plus k, should be positive, so that they should be greater than 0. That is what is shown here. I am considering 8 minus k to be greater than 0 and 1 plus k to be greater than 0. So when we solve for this value of k, we are going to get two values for k as minus 1 and 8. So the condition for the stability is that if k value lies between minus 1 and k, the system is said to be stable. So like this, we can just determine the DC gain value for a system for which the system might become stable. So these type of questions are expected in the examination usually. Now, so a system with equations will be given, or with a block diagram might be given. So here there is a block diagram which is given to us with an open loop transfer function as 1000 divided by s plus 2 into s plus 3 into s plus 5. Now whenever the feedback here is considered to be 1, so whenever a system is given like this, the first thing is you need to solve and find out the closed loop transfer function. So here we are getting the closed loop transfer function as 1000 divided by s square plus 10s square plus 31s plus 1030 as our closed loop transfer function. Now you have to construct the roots table using the procedure, and if you can observe here, the value what I've got is 1 1 minus 72 103 first column, here 31 103 0 0 0 0 0 0. Okay, now here as you can observe there are two sign changes. So 1 to 1, 1 to minus 72, minus 72 to 103. So there are two sign changes. So system is said to be unstable since two roots are changing the sign, and the two roots are said to be lying in the right half of the S-plane. System is said to be unstable. So few more examples are quoted in the similar way. So your equation is 2s to the power 4 plus s cube plus 3s square plus 5s plus 10 equal to 0. We have constructed the roots array. So in this example also you can observe that there are two sign changes. That is, you have in the first column you have 2 1, from 1 you are changing to minus 7, and from minus 7 you are changing to 6.43. So two sign changes. System is said to be unstable for this example also. Now coming to a 0 only in the first column. So if you have, for example, a 0 in your first column, what will happen? Okay, so if the first element in any of the row is 0, then division by 0 will give us an infinity value. So to avoid this, we are going to follow one epsilon, a small positive number which will be replacing it, and then we will construct the next consecutive rows, and then we are going to evaluate the epsilon value. So here this is in case wherein I will get a 0 here in the third column. Okay, that is in the third row, sorry. So here this is replaced with epsilon, and then we are going to construct the next consecutive rows using that epsilon value, where c1 is obtained as 4 epsilon minus 12 by epsilon, which is nothing but equal to minus 12 by epsilon. And similarly d is taken as 6c1 minus 10e by c1, which you will be getting it as equal to 6. So you can observe that 1 2 epsilon is considered to be positive. From epsilon to c1 you have one sign change, from c1 to d1 you have another sign change. So legally, by treating epsilon to be a positive value, we are able to get two sign changes, and system is said to be unstable. This is the case wherein you will get any one of the element in the row, that is first element in the row, as equal to 0. So this is one procedure what we can adopt. Okay, so example for the same procedure is shown here, wherein again here I have a 0 value which is replaced with epsilon, and we have evaluated the two values, that is c1 and k, and you can observe that c1 is negative. So here also there are two sign changes, and system is said to be unstable. So here an equation is given, and we are trying to construct the table. Same procedure almost, so you can refer this later. So next procedure is reversing the coefficient. So here in the previous procedure we have replaced 0 with epsilon, but here what we will do is, if we get a 0 in the uh, first column, then another procedure that we can adopt is reverse coefficient procedure. Here what we will do is, a polynomial that has a reciprocal roots of the original polynomial has its roots distributed uh, in the right half plane or left half plane or on the imaginary axis, because taking the reciprocal of the root value does not move it to another region. So if we can find a polynomial that has the reciprocal root of the original, it is possible that root table for a new polynomial will not be 0 in the first column. So this could be avoided. So computationally this method is considered to be easier than the epsilon method. So here what we will do is, you will write your equation from the reverse side. That is, here we are, the equation is what, s to the power 5 plus 2 s to the power 4 plus 3 s cube plus 6 s square plus 5s plus 3. So I'll just write my equation in a reverse way like this. That is, I'll start from this end. So write your equation from this end, considering this to have a highest power. That is what is called as the reciprocal equation. So I can rewrite my equation as 3s to the power 5, 5s to the power 4, 6s cube plus 12s square plus 2s plus 1. Just reverse your equation with the power of s. Now take the coefficient and construct the roots table. So if you take these coefficient and construct your root table, you will not get any zero value in the first column, and you can observe that there are two sign changes. If you can see, 3 to 5 no sign change, 5 to 4.2 no sign change, 4.2 to 1.3 no sign change, 1.33 to minus 1.75 one sign change, and minus 1.7 to 1 more sign change. So there are totally two sign changes. So system is said to be unstable if you have any changes in the first column of the roots array. So that is why system is said to be unstable, and you have two roots which lie in the right half of the S-plane. So we can notice that the table does not have any zero value in the first column if we reverse the equation by taking the reciprocal. Okay, now this is another case wherein you might have a case wherein your entire row could be zero. So this might also happen. So this also gives us erroneous results, because the next row might become infinity, because you'll be dividing it by 0 and we cannot construct the array. So in such cases, what we will do is we are going to construct an equation called as auxiliary equation. Okay, so or auxiliary polynomial. So here if you can observe, in this table I have got an equation with all zeros. See here, this 0, 0, 0. In such cases, what we will do is we are going to construct the polynomial equation using the previous row elements. That is, your previous elements are 7, 42 and 56, right? Okay, we have these values. So your elements here, what I am going to get will be s to the power 4 plus 6 s square plus 8. Okay, this is our value which we are going to get by dividing it by 7. Okay, so your polynomial equation or your auxiliary equation is represented as p of s. In some of the books they will take that also as equal to a of s. It's equal to s to the power 4 plus 6s square plus 8s. Now we will differentiate this equation with respect to x, so that I'll get the value as 4s cube plus 12s plus 0. Now this value 4 and 12 is replaced here. Okay, and you will construct your next row elements, and you will analyze the stability of the system. Okay, so since we have 4 and 12, it could be divided by 1 by 4, and you can take that as equal to 1 and 3, and you can just check that when you construct your next row, you are going to get the value as equal to 1 by 3, 0, 0. Here it is 8, 0, 0. Okay, and this row you are going to get it as equal to 3 and 8. So if you can observe this column, there are no sign changes and system is said to be stable. So one more example I am taking here, wherein you are supposed to determine the k value. So here we are going to construct the roots array, and then we will verify whether the elements in the first column are all positive or negative, or there are no sign changes. So for value of k between 0 to 8, we are going to get the uh, stability for the system for this particular example. So this is another case wherein I will be getting the entire row again as equal to 0. Okay, so this is an example of a polynomial which gives us a value as equal to 0. So whenever the entire row is 0, this tells us that symmetry can occur under three conditions of the root position. That is, roots are symmetrical and real, roots are symmetrical and imaginary, or roots are quadratical. These are the cases which may lead to an entire row with 0 value. So each case or combination of these cases will generate an even polynomial. So the row of zeros tells us the existence of even polynomial whose roots are symmetric about the origin, and in some cases some of the roots could be on the j omega axis also. On the other side, if j omega roots are symmetrical about the origin, and if we do not have a row of zeros, we cannot possibly have a j omega roots. So another characteristics of root table is that the row previous to the row of zeros contains the even polynomial, that is a factor of original polynomial. And finally, everything from the row containing the even polynomial down to the end of the root table is the test of the only even polynomial. So this is an example where I am taking an equation which is given as 20 divided by s to the power 8, s to the power 7 plus 12 s to the power 6, 22 s to the power 5 plus 39 s to the power 4 plus 59 s cube plus 49 s square plus 38 s plus 20. So for the equation given to us, this is the roots table which we are getting. And after simplification, we'll just verify the first column to check the sign changes. So if you can observe here also, we have two sign changes, and system is said to be on. The system is said to be here unstable because you have two roots which lie in the right half of the S plane. So this is another example which is quoted. Okay, so the main things that we have to remember here is how do we know the interpret in the roots table is that since all the entries from the even polynomial at s to the power 4 row down to s to the power 0 are a test of the even polynomial, we begin to draw some conclusion about the roots of the even polynomial, that is no sign changes exists from s to the power 4 row to s to the power 0. That's the even polynomial does not have right half plane poles. Okay, and since there are no right half plane poles, no left half plane poles are present because of the required symmetry. Hence the even polynomial must have all the four of its poles on the j omega axis. So these are the summarized results of the previous example what we have quoted. Now coming to the almost we have come to the end of session. So here these are some reference books which you can refer for the problems. And in today's session, as you know, we have learned about an important criteria called as roots criteria, which helps us to analyze the stability of the system, and we have dealt with few examples and special cases that we can encounter during the stability analysis of the system. Thank you all. Have a nice day. Jai Shri Gurudev.